Okay, let's dive in. We've got this huge stack of source material today. And look, we're not here to rehash basic CRD.
No, absolutely not.
We're aiming higher. We're
Yeah.
talking L6, L7 engineering level mastery of MongoDB. The architecture, the deep operational stuff, the math underneath it all.
That's exactly the plan. We're synthesizing, a massive amount of information, giving you the shortcuts through, well, everything from CAP and RAF theory,
Right.
down to the wider Tiger engine internals, MBCC, and how you actually tune this beast in production at scale.
Yeah, the goal here is to pull together these 17 critical topics from the sources. We want you, listening, to walk away really getting the trade-offs. Not just how it works, but why certain decisions are made.
Yeah.
That's the architect mindset.
Couldn't agree more. So where do we start? Has to be the foundation, right? Distributed systems theory.
Let's do it. Part one, the theoretical backbone, consistency and availability.
Any distributed database conversation, it really has to start with the CIP theorem. Eric Brewer's idea. It's this fundamental compromise.
The unavoidable choice.
Exactly. When you've got a network partition, a failure, you can only fully guarantee 2 out of 3 things: consistency, availability, or partition tolerance.
Okay, let's just quickly nail those down for everyone. CAP.
Right. Consistency C means every read gets the absolute latest right. Like all nodes see the same current state instantly.
Okay.
Availability A is simpler. Every request gets a response, a non-error response, reasonably quickly. The system always answers the phone.
Always on.
And partition tolerance, P. Well, that's the reality of networks. It means the system keeps working even if messages get lost or nodes get cut off from each other.
Which, let's be honest, always happens eventually in distributed systems.
Always. So the theorem says you must tolerate partitions if you want a distributed system. The real choice is C versus A when P happens.
And the sources are very clear where MongoDB plants its flag, initially at least.
Yep.
But I want to push on this a bit. It's fundamentally CP, right? Consistency plus partition tolerance.
That's the default, yes. When a partition hits, MongoDB will choose consistency. It sacrifices availability. It has to.
But here's the L6 engineer question. Don't most production setups immediately start tweaking it, pushing it towards AP for practical reasons?
Ah, yes. That's exactly the advanced discussion. It defaults to CP, meaning the minority side of a partition becomes unavailable for writes to guarantee no data conflicts. But understanding how you can tune it towards AP behavior, using read and write concerns, and crucially, what risks you're taking on, that's where the real architectural skill comes in.
Okay, before we get to the tuning risks, let's lock down the safety mechanism, the quorum mechanics. How does the math stop the dreaded split brain?
Quorum is the core safety net. It's derived from RAF consensus principles. Simple rule, if you have n nodes in your replica set, you need a majority, specifically $, floor, n2 floor plus $1 nodes talking to each other to form a quorum.
So 3 nodes need 2, 5 nodes need 3, 7 nodes need 4. That math.
Exactly that math. If a network splits a 5-node set into, say, a group of 3 and a group of 2, only the group of 3 can elect a primary and continue accepting writes. The group of 2, it becomes read-only, unavailable for writes.
And that simple majority rule is the mathematical guarantee that prevents 2 different nodes from simultaneously thinking they're the primary. No split brain.
Precisely. The minority side just stops. It sacrifices that immediate availability to ensure that when the network heals, there's only one unambiguous source of truth, the primary on the majority side.
Okay, it makes sense. Now, back to the production reality. That high-traffic e-commerce site example. Uptime is king. How do I use that tunability? How do I consciously slide MongoDB closer to AP?
You do it by adjusting the write concern and the read concern. These are the knobs. If you set your write concern to W1, you're telling the system, just wait for the primary to acknowledge this write. Don't worry about the secondaries yet.
Super fast acknowledgement.
Very fast. Then, if you combine that potentially risky write with, say, local reads reading from whatever node is nearest primary or secondary, you've basically maximized responsiveness. Partitions are less likely to block you.
But you use the word risky. That W1 setting sounds dangerous. What's the specific failure mode?
Oh, it's absolutely fraught with danger. You've made an explicit choice. Availability now matters more than guaranteed data integrity during that potential partition window.
So what happens?
A write acknowledged with W1 could be sitting only in the primary's memory. If that primary clashes, like immediately after sending the OK back to the client, but before replicating that write to any secondaries,
Oof, gone.
that write is lost forever, even though your application thought it was saved. And local reads. You risk reading stale data from a secondary that hasn't caught up yet. It's a conscious acceptance of potential data loss or inconsistency for lower latency and higher uptime. Big trade-off. Hashtag tech 1.2 ACID properties in a distributed context.
Okay, let's switch gears slightly. Transaction guarantees. ACID. MongoDB's initial strength was always single document atomicity, right? That was built into WiredTiger.
Correct. Any update affecting multiple fields within a single document was guaranteed to be all or nothing. That's a core benefit of the document model plus MACC.
But the game changed significantly around MongoDB 4.0, 4.2. We got multi-document atomicity. Transactions that can span multiple documents, multiple collections, even multiple shards. That's a huge leap in complexity. What's the underlying mechanism?
The main mechanism is snapshot isolation, adapted for a distributed world. Instead of traditional locking, when a multi-document transaction starts, the system takes a cluster-wide, consistent snapshot timestamp.
Like a photograph of the database state at that instant.
Exactly. The transaction then operates against that snapshot. It only sees data that was committed before that timestamp. This prevents dirty reads, non-repeatable reads, phantom reads, all those concurrency nightmares, but across potentially many documents and shards.
Now, within ACID's isolation hive, the sources mentioned 4 distinct mechanisms or levels. We've hit snapshot isolation for the multi-doc transactions. What about session causality? Why is that important?
Session causality is more about user experience, really. It guarantees that within a single client session, if you write something, you're guaranteed to be able to read it back immediately.
Read your writes.
Read your writes, precisely. You won't get that weirdness where you update your profile, hit refresh, and see the old data because you happen to hit a replica that hadn't received the update yet. MongoDB manages this using causal consistency tokens passed between the client and server within a session.
Okay, that makes sense. But the real tuning knobs, the ones where L6 engineers earn their keep, seem to be the read concern variations, moving beyond local and available.
Right. Local and available are fast, potentially reading from secondaries, but they carry that risk of stale or uncommitted data we talked about. For safety, you start with majority.
Read concern majority, what does that guarantee?
It guarantees that the data you read has been successfully written to and acknowledged by a majority of the replica set members. So it's durable, it won't be rolled back due to a primary failure. It's the baseline for reliable reads.
But then there's the ultimate level, linearizable. The sources call this highly technical. What makes it so special, and how does it work without bringing the system to its knees with global locks?
Linearizable is the absolute strongest guarantee. It basically makes the distributed system behave as if it were a single machine operating in real time. If Operation A finishes before Operation B starts, B must see the result of A.
How? What's the mechanism?
It involves reading from the primary, but then, critically, the primary performs an additional check after the read. It confirms with the majority of the replica set nodes that it is still the primary and that no subsequent write that might have occurred concurrently has been committed by a newer primary since the read began.
Wow. Okay, so it's like a read followed by a quick consensus check.
Essentially, yes. It ensures perfect real-time ordering. If 2 writes happen milliseconds apart, linearizable reads will always reflect that order. The cost, obviously, is latency. That extra consensus check adds overhead to the read path. You pay for that perfect ordering.
Performance cost is definitely real there. Okay, final ACID property. Durability D. If I need absolutely zero data loss tolerance, my recovery point objective, or RPO, needs to be near zero. How is that guaranteed?
Durability in MongoDB is tied directly, almost entirely, to the write concern. We already touched on W1 being risky.
High risk of data loss on primary failure.
Exactly. Your RPO is definitely non-zero there. To get to near zero RPO, you must use W majority. This ensures the write is persisted on a majority of nodes before the acknowledgement is sent back. If the primary fails, the data is safe on the other nodes.
What about that extra flag sometimes mentioned, W majority, J true? Does the J true add significant extra safety?
The J-true forces the write to be flushed to the on-disk journal on the majority of nodes before acknowledging. Modern systems with WiredTiger usually journal quickly anyway, so the practical difference between J-false, that a default with majority, and J-true is often minimal in terms of actual risk. However, J-true provides that absolute explicit guarantee against data loss, even if the OS buffer cache itself were somehow compromised across the majority simultaneously before a flush.
So it's the ultimate belt and suspenders approach.
Pretty much. You pay a slight extra latency penalty for that absolute certainty. Again, it's something you'd model and test carefully before enabling globally. It's all about those trade-offs.
All right, let's tackle a fundamental CS problem in distributed systems. Time. Or rather, the lack of perfectly synchronized time. We need logical clocks. The sources start with the simpler one, Lamport clocks.
Right, Leslie Lamport's idea. It's a way to bring some sense of order to events scattered across different machines without needing perfectly synced atomic clocks. It's a scalar clock, just a single integer counter, let's call it $.
How does it work? The rules.
Simple rules. First, every time a process has an internal event, it just increments its own counter dollars. Second, when a process sends a message, it attaches its current counter value, $2, to the message. Third, when a process receives a message with timestamp $2, it updates its own counter dollar to be the maximum of its current value and the received timestamp $2, and then increments dollars. So $2 are max plus a long.
Okay, and this gives us the crucial property. If event A happens before event B, meaning A caused B, maybe by sending a message, then the Lamport clock value of A will always be less than the Lamport clock value of D LCAA.
Correct. It captures the causality in that direction. If A precedes B causally, its timestamp is smaller.
But the sources stress this heavily. The reverse is not true. Just because LCA, LCB, it doesn't automatically mean A caused B.
Exactly. That's the key limitation. A and B could be completely concurrent, independent events that just happen to get assigned timestamps, where A's is smaller. Lamport clocks provide a total ordering of all events, which is useful, but it doesn't perfectly distinguish between true causal succession and mere accidental ordering of concurrent events.
Which leads us to the more powerful but much heavier alternative, vector clocks.
Vector clocks fix that ambiguity. Instead of a single counter, each process maintains a vector of counters, one entry for each process in the entire system. Let's say there are nodal processes. Each process dollars has a vector of size dollar.
So V tracks its own events, and V tracks the latest event it knows about from process dollars.
Precisely. When process dollars has an event, it increments a message. It sends a message, it sends its entire current vector V dollars. When process Y receives a message with vector dollars, it updates its own vector V dollars by taking the element Y's maximum of V dollars and then increments V dollar.
The power here is in comparing to vectors, say V dollar and V just $2. We can tell exactly if V dollars happened before V dollars or V dollars before V dollars
or if they happen concurrently. That's the big win. $1 causally precedes V tau 2 if every element in $1 is less than or equal to the corresponding element in VD tau 2, and at least one element is strictly smaller. They are concurrent, V tau 2, if neither causally precedes the other. Vector clocks perfectly capture causality.
Okay, sounds amazing. Why doesn't MongoDB just use vector clocks everywhere then?
Yeah.
The sources hinted at a major drawback.
Scalability. It's the overhead. Imagine a sharded cluster with, say, 1,000 shards. That means $1,000, sir.
Right.
Every single internal message, every replication event would need to carry a vector of 1,000 integers. That's a massive overhead in terms of message size, bandwidth consumption, and storage. It just doesn't scale well for large systems.
Ah, okay. So MongoDB uses simpler Lamport-style version numbers internally, like in the oplog and MVCC, and relies on the stronger guarantees from quorum rights, W.majority, to handle the trickier cross-node consistency issues, avoiding the vector clock overhead.
That's a good summary of the practical compromise, yes.
Okay, let's transition from the abstract theory to the metal, the actual engine, starting with the data format itself, BSON. Why not just use JSON? Hashtag tag 2.1 BSON and the document model.
BSON binary JSON is fundamental. JSON is great for human readability and web APIs, but for a high-performance database engine, it's actually pretty inefficient.
What are the specific advantages? The sources listed 3 key ones.
Number 1, size efficiency. BSON stores numbers, dates, binary data in compact binary formats like a 64-bit integer or float instead of variable length strings like 123.45, saves a lot of space, especially with numerical data.
Makes sense.
Number 2, type safety. BSON explicitly encodes the data type along with the value. For e.g., this is a 32-bit int, this is a string, this is a date. JSON is typeless in comparison, which can lead to ambiguity.
Right, everything can look like a string in JSON.
And number 3, arguably the most important for performance, faster parsing. BSON includes length prefixes for documents and elements. This means the engine can scan a BSON document and jump directly to a specific field it needs without having to parse everything that comes before it.
Like random access within the document. Huge for index lookups or projections needing only a few fields.
Absolutely critical. But this structure and the way MongoDB manages documents leads to that famous, sometimes infamous limit, the 16 MB maximum document size. Why that specific number?
Yeah, why 16 MB? Seems arbitrary.
It's not arbitrary. It's a pragmatic engineering decision based on several factors. First, memory pressure. Processing a single huge document requires allocating a large chunk of contiguous RAM. Manipulating it, applying updates, comparing versions in MVCC, it all gets much harder and potentially fragments memory with enormous documents.
And the MVCC aspect is key, right? Wired Tiger needs to store old versions.
Exactly. Imagine a 1 GB document. Trying to maintain multiple versions of that for snapshot isolation. Your history store would explode, consuming vast amounts of RAM and disk, leading to terrible performance. It keeps transaction atomicity manageable within the storage engine.
Okay, memory and MVCC. What else?
Network manageability, sending huge documents over the wire, is slow and resource intensive. And index entry size, if a large document is indexed, the index entry itself can become bloated. The 16 MeMe limit forces a design pattern. If your data entity is naturally larger, you should probably be using GridFS.
Which breaks the large file into smaller, manageable chunks stored in separate collections.
Correct. GridFS is the intended solution for large binary objects, not massive single documents.
Let's talk about the default ID, objected, that 12-byte value. What's the engineering brilliance behind its structure? It's not just about uniqueness.
Right, the 12 bytes are cleverly packed. The first 4 bytes are a Unix timestamp, seconds since the epoch. This is great because it means objected sort chronologically, which is incredibly useful for indexing and querying time-based data. You get a roughly time-ordered insertion pattern.
Okay, 4 bytes timestamp. What's next?
The next 5 bytes are unique identifiers for the machine and the process that generated the ID. This helps ensure uniqueness across a distributed cluster.
So machine process ID, that leaves 3 bytes.
The last 3 bytes are a simple incrementing counter, initialized with a random value per process. This handles uniqueness for IDs generated within the same second on the same process.
The big advantage here is distributed generation, right? Clients or app servers can create object ads without needing a round trip to the database to ask for the next ID.
Exactly. Massive win for insert performance and scalability, no central ID generator bottleneck.
But there's a subtle disadvantage, particularly for indexes, isn't there? The non-sequential nature of that counter across different processes.
Yes, that's the trade-off. While the timestamp gives you mostly sequential ordering, the counters across different machines are not synchronized. So if you have many application servers inserting concurrently, the object key is generated but won't be perfectly sequential. This can lead to slightly more index page splits and fragmentation compared to, say, a perfectly sequential UUID generator, potentially impacting index efficiency over time. It's usually a minor effect, but something to be aware of. Hashtag tag 2.2 wire tugger and MVCC snapshot isolation, the true deep dive.
Okay. Now for the heart of MongoDB's performance. The WiredTiger storage engine and its implementation of MVCC multi-version concurrency control. Let's really dig deep here. At a fundamental level, what problem does MVCC solve compared to older database locking strategies?
The core problem with traditional locking is contention. If a writer needs to update some data, it often takes an exclusive lock, blocking out all other readers and writers until it's done. This creates bottlenecks. MVCC avoids this by, well, using multiple versions.
So instead of locking, it uses versioning. How does that work?
When data is modified, WiredTiger doesn't overwrite the old data immediately. Instead, it creates a new version of the document, or the relevant pages, and links it into a version chain. The old version is kept around for a while.
So reads and writes can happen at the same time.
Yes, that's the magic. A reader transaction that started before the write began will simply see the older version of the data. A reader transaction starting after the write commits will see the new version. They operate on different, consistent views of the data without blocking each other. Reads don't block writes, and writes don't block reads.
Okay, let's get precise about visibility. A read transaction starts, and it gets assigned a snapshot timestamp. Let's call it $2. How does the engine decide which version $5 of a document created at time to biller should be visible to this reader?
The snapshot visibility function is actually quite simple and strict. A version $, created at $2 is visible to a transaction reading at snapshot time $2 if and only if $2 is less than $2. The transaction only sees versions that were committed before it started.
Crystal clear. It gets a consistent view of the past. What happens, though, when two transactions, say transaction A and transaction B, try to write to the same document concurrently based on the same initial snapshot? That must cause a conflict.
It does. This is where write conflict detection comes in. WiredTiger uses optimistic concurrency control, OCC. Transactions proceed assuming conflicts are rare. When transaction A goes to commit its changes, WiredTiger checks. Has any data that transaction A read been modified and committed by another transaction, like B, since A's snapshot 10 was taken?
And if the answer is yes,
If a conflict is detected, one of the transactions must fail. Typically, the transaction attempting to commit later, say, A, will receive a write conflict error or a snapshot isolation error. It's forced to abort and roll back its changes. The application then usually needs to retry the entire transaction.
and that rollback mechanism for the engineers debugging this stuff, how is that managed internally? Undo logs.
Yes, WireTiger maintains undo information. As a transaction makes changes, the engine records how to reverse those changes. If the transaction successfully commits, the undo info can eventually be discarded. If it aborts due to a conflict or error, the engine uses that undo information to efficiently revert the database state back to how it was before the transaction started, ensuring atomicity.
This leads directly to a major operational headache, if not managed. The history store and eviction. Old versions have to be cleaned up, right?
Absolutely critical. Those old document versions we mentioned. They're kept in a specific part of the cache and on disk called the history store. They are essential for providing those consistent snapshots to older, still running transactions.
But they can't stay there forever. How does garbage collection work?
A version becomes eligible for garbage collection, eviction, only when WireTiger determines that it is no longer visible to any active transaction snapshot in the system. The engine keeps track of the oldest active snapshot timestamp. Any version older than that oldest timestamp is potentially reclaimable.
And here's the operational nightmare. The long-running transaction, like a big analytics query or backup that runs for an hour.
Exactly. That transaction holds on to its initial snapshot timestamp for the entire hour. This acts like a dam, preventing the garbage collector from cleaning up any versions created after tenant time but before the current time, even if those versions were updated thousands of times.
So the history store just grows and grows.
It bloats, consumes potentially huge amounts of RAM, pushes useful data out of the main cache, leads to cache thrashing, constantly reading old versions from disk, and dramatically slows down the entire system. Monitoring for and managing long-running transactions is absolutely vital for maintaining WiredTiger performance. Hashtag 2.3 checkpoint algorithm.
Okay, so MVCC handles concurrency. What ensures the data actually makes it durably to disk in a consistent state for recovery? That's the checkpoint algorithm. Walk us through that process. It's not just a simple flush, is it?
No, it's more nuanced to minimize performance impact. Checkpoints are periodic operations, typically every 60 seconds by default, that create a consistent snapshot of the database on disk. This is the point from which recovery would start if the server crashed uncleanly between checkpoints.
What are the steps involved? There are locks, right?
Yes, but they try to minimize the impact. First, WireTiger acquires a fuzzy lock. This is a lighter weight lock.
What does fuzzy mean here? What does it allow?
It allows the process of identifying dirty pages, data changed in memory but not yet on disk, and starting to write them out to disk to happen in the background, while still allowing normal read and write operations to continue. This does the bulk of the I/O work without a hard pause.
Okay, so most of the flushing happens under the fuzzy lock, but you need a perfectly consistent point.
Exactly. To mark that truly consistent point on disk, the system must, very briefly, acquire a global exclusive lock. This lock does pause all incoming application reads and writes.
The brief pause. That's the latency spike we sometimes see.
That's the one. During this short exclusive lock window, hopefully just tens or maybe hundreds of milliseconds depending on load, WiredTiger finishes flushing any remaining critical changes, updates metadata, writes the checkpoint marker to disk indicating a consistent state, and then releases the exclusive lock. Operations resume immediately.
So if I'm troubleshooting and see regular latency spikes exactly every 60 seconds, the checkpoint is the prime suspect. It's the cost of flushing those accumulated dirty pages.
Absolutely. The checkpoint provides the stable on-disk recovery point, essential for durability. For recovering changes between checkpoints after a crash, that's where the journal, or write-ahead log, comes in. It logs changes rapidly and allows replaying them from the last checkpoint forward. Checkpoints handle the baseline durability. The journal handles the fast recovery gap.
Right, we've got the core engine down. Now, how does MongoDB use this engine to build systems that stay up, high availability, and handle massive amounts of data? Scalability. Let's start with HA via replication. Hashtag 3.1 replication and Raft-inspired consensus.
For replication and ensuring consistency across replicas, MongoDB employs a consensus protocol that's heavily inspired by Raft.
Why Raft? The sources mention Paxos is notoriously complex.
That's exactly it. Raft was designed specifically with understandability and implementability in mind. Compared to Paxos, its state transitions and leader election process are generally considered easier to reason about, implement correctly, and critically debug when things inevitably go wrong in production. Simplicity leads to robustness here.
Raft revolves around key concepts like the term and the voting process for leader election. Can you break those down?
Sure, a term is like an epoch or a generation number for the cluster. It's a monotonically increasing integer. Each term starts with an election. If a node, a follower or candidate, doesn't hear from the current leader for a certain timeout, it increments the term number and starts an election for that new term.
And to win the election and become the primary for that term.
It needs to get votes from a majority of the nodes in the replica, set that same floor, N2 air floor, plus a lunicorn quorum we discussed earlier. The term number is crucial because it acts as a logical clock. If a node receives a message with a higher term number, it immediately reverts to being a follower and accepts the new leader. It prevents stale leaders from causing chaos.
And the actual data replication, the mechanism ensuring secondaries get the rights from the primary, relies entirely on the op log, right?
Absolutely. The op log, operation log, is fundamental. It's essentially a special capped collection stored on each replica set member. The primary writes a record of every single database modification, inserts, updates, deletes, to its op log first.
Sequentially, idempotently.
Yes, each entry gets a unique timestamp identifier. Secondaries then constantly tail the primary's op log, reading these operations in order and applying them to their own data sets. This is how they stay synchronized.
From an operational perspective, especially for L6, L7 engineers managing large clusters, what's the single biggest danger associated with the op log?
Oplog retention size or duration. The oplog is capped, meaning older entries are eventually discarded to save space. Now imagine a secondary node goes offline for maintenance or gets disconnected due to a network issue.
Yeah.
The primary keeps processing writes and adding entries to its oplog. If the secondary is disconnected for too long, it might fall so far behind that the primary's oplog no longer contains the first operation the secondary needs to resume replication. The necessary starting point has been aged out and deleted.
And when that happens, the secondary is essentially lost. It can't catch up incrementally.
Exactly. It enters a state called recovery, or fatal. The only way to bring it back into sync is a full initial sync. It has to wipe its entire data directory and copy all the data from the primary, or another up-to-date secondary. This is incredibly resource-intensive network bandwidth, disk I/O, CPU, and can take hours or even days for very large data sets.
So job number one is monitor replication lag and ensure your oplog size, usually configured by time like 24 hours or by size in GB, is significantly larger than your expected maximum downtime or recovery window.
Absolutely non-negotiable for HA.
Let's quickly loop back to consistency guarantees, specifically the dangers. We talked about W.1 being risky. Can you paint a clear picture of data loss, a concrete scenario?
Sure. Imagine an online order system. A customer places an order. The application writes the order details to MongoDB with write concern W.1. The primary node receives the write, logs it perhaps only to its journal or memory, and immediately sends OK back to the application. The app tells the customer, order confirmed.
Okay, sounds fine so far.
But 1 millisecond later, before that primary has replicated the order to any secondary nodes, the power supply on the primary server fails catastrophically. It's gone.
The replica set holds an election.
Exactly. The remaining secondaries elect a new primary amongst themselves, but none of them ever receive the write for that customer's order. When the new primary comes online, that order data simply doesn't exist. It was acknowledged to the client, but then permanently lost due to the primary failure before replication completed.
That's the W1 gamble. You trade that risk for lower latency.
Precisely why subatomic majority is the default and recommended setting for any data you cannot afford to lose. It forces the write to be durable on multiple nodes before confirming success.
And let's quickly reemphasize linearizable reads. We know it uses that extra sync check. Why is that check superior to just doing a majority read concern? Doesn't majority already guarantee durability?
Majority guarantees durability, the data won't be rolled back, but doesn't guarantee real-time ordering relative to concurrent writes. You could issue a majority read and milliseconds later a write could commit to the majority, but your read might not see it because it snapshot slightly earlier. Linearizable closes that gap. By performing the read and then checking with the quorum that it's still the leader and no newer writes relevant to the read have completed, it ensures the read reflects the absolute latest state of the cluster as if all operations happen sequentially in real time.
Guarantees you read something at least as recent as any write that completed before your read started. the strictest ordering.
Exactly. It eliminates that tiny window of ambiguity at the cost of that extra read path latency.
Okay, high availability is covered by replication. But to handle truly massive data volumes or write throughput, we need sharding, splitting the data across multiple replica sets, shards. The magic behind keeping data balanced across these shards is the balancer.
The balancer process is key. It typically runs on the primary node of the config server replica set. Its job is to monitor the distribution of data chunks across the shards and initiate migrations to even things out when necessary.
How often does it check? And what's the logic? How does it define an imbalance? It's not just about the raw number of chunks, is it?
It usually runs its check cycle every 30 seconds or so. The imbalance calculation isn't just a simple count. It looks at the difference in the number of chunks between the shard with the most chunks and the shard with the fewest chunks for a specific sharded collection. The exact threshold for triggering migration depends on the total number of chunks in the collection. It's dynamic.
So for a small collection, maybe a difference of 2 chunks triggers a move, but for a massive one, it might need a difference of 8 or more.
Something like that, yes. The goal is to avoid unnecessary migrations for tiny fluctuations, but react when a genuine imbalance develops. When the threshold is breached, it selects a chunk or chunks to move, prioritizing moving from the most loaded shard, the donor, to the least loaded shard, the receiver.
Let's talk about the chunk migration process itself. This has to happen without taking the application offline. That implies a fairly complex dance between the donor and receiver shards.
It's a well-orchestrated multi-step process designed for minimal impact. First, the balancer tells the donor shard to start migrating a specific chunk range to the receiver. The receiver then starts copying the documents within that chunk range directly from the donor.
While the donor is potentially still receiving writes for that chunk.
Yes, exactly. That's step one, the bulk copy. Step two is crucial. While the copy is happening, the donor shard keeps track of all new writes coming in for that specific chunk range using its op log. The receiver continuously fetches and applies these ongoing changes from the donor's op log to catch up.
So it's copying the history and then replaying the recent changes.
Right. It keeps doing this until it's nearly caught up. Then comes step three, the critical final phase. The donor shard briefly blocks writes only to the chunk being migrated. It transfers the last few oplog entries, confirms the receiver has them, and then updates the cluster's routing metadata on the config servers to say, this chunk now lives on the receiver shard. Then it releases the lock.
And that brief write block in step 3, that's the source of those small latency spikes people sometimes observe during migrations.
That's typically it. It's usually very short, maybe tens of milliseconds, but it's necessary to ensure atomicity during the final handoff, a key operational point. The entire migration process relies heavily on the config servers. If the config server replica set loses quorum, all balancing activity halts immediately. Config server health is paramount for sharding.
Okay, now for the bane of sharded clusters. Jumbo chunks. The sources called them the scaling killer. What causes a chunk to become jumbo, and why can't the balancer just split it?
A jumbo chunk is a chunk that contains more data than the configured maximum chunk size, for example, 64 MB or 128 MB by default. Or R, crucially, contains documents whose shard key values span a range that cannot be split further without exceeding the maximum number of documents allowed per chunk range to be migrated. The primary cause is almost always a poor choice of shard key.
Like what kind of poor choices?
Two main culprits. First, monotonic shard keys. Using something like an incrementing order ID or a timestamp as your shard key, all new inserts pile into the same chunk on the same shard, the one holding the highest range. That single chunk grows indefinitely, becoming jumbo, while other shards sit idle. It's append-only growth on one shard.
The classic hot shard problem. What's the second cause?
Keys with low cardinality. Imagine sharding your user collection by country, but 90% of your users are in just 3 countries. You can add 100 shards, but your data will only ever live on, at most, 3 of them because the shard key simply doesn't have enough distinct values to spread the data out. Chunks associated with those high-volume countries will likely become jumbo and indivisible.
Detecting them involves checking config.chunks for the jumbo. True flag. Fixing them used to be a nightmare, involving manual splits or downtime. What's the modern L6L7 approach now?
The game changer is online resharding, introduced in MongoDB 5.0. This allows you to change the shard key for a collection or refine it while the application is running. MongoDB copies the data in the background, rebuilding it according to the new shard key definition, and transparently switches over when complete. It's the definitive solution for fixing historical shard key mistakes, including those leading to jumbo chunks without requiring an outage.
Okay, let's shift into real-world production operations, disaster recovery, and the newer features. Data safety always starts with backups and recovery. Hashtag check 4.1 backup PITR and disaster recovery, DR right.
MongoDB offers a few backup approaches. There's logical backup using MongoDump. It's simple, produces human-readable output like BSON files, good for smaller data sets or migrating between versions, but it's slow for large clusters, as it has to read all the data through the query engine.
Then there are faster methods.
Yes, physical backups. This usually involves taking file system snapshots using LVM, ZFS, cloud provider snapshots, etc., of the underlying data files. This can be much faster, especially for multi-terabyte clusters because you're copying blocks directly. But you must ensure the snapshot captures a consistent state of the wired tiger files, often requiring a brief lock or using the synclock command.
And the third type.
Incremental backups. These typically combine a full physical snapshot taken periodically, say daily, with continuously archiving the oplog entries generated between snapshots. This allows for faster restores and, crucially, point-in-time recovery.
Let's talk about point-time recovery, PITR. This seems essential for recovering from, say, accidental data deletion or a bad deployment. How does it work mechanically?
PITR lets you restore the database to a specific moment in time, often down to the second. The process starts by restoring the latest full backup snapshot, logical or physical, taken before your desired recovery point. Then you take the archived oplog entries generated after that snapshot and replay them, applying all the changes sequentially, stopping precisely at the target timestamp you want to recover to.
Simple concept,
Yeah.
but it hinges entirely on having those oplog entries available, right?
Right.
This brings us back to oplog retention.
Absolutely critical dependency. If you take a full backup every 24 hours, you must ensure your oplog retention, either on the live nodes or in your backup archive, covers at least that 24-hour period, plus a safety margin. If your oplog only holds 12 hours of history, but your last backup is 20 hours old, you simply cannot perform PITR for any time within that 8-hour gap. You've lost the necessary history. Oplog window must exceed the backup interval.
Okay, let's apply this to a concrete DR scenario from the sources. Designing for a 5-shard cluster, needing an RPO, recovery point objective, under 1 minute. What does that architecture look like?
RPO 1 minute essentially means near zero data loss tolerance for committed writes. The first requirement is using write concern majority for all critical operations. That ensures the write is durable across the primary's region before acknowledgement.
Okay, majority writes handle local durability. What about site failure?
For site failure or regional disaster, you need multi-region replication. You'd typically set up your replica sets spanning multiple availability zones or even geographic regions. But for sophisticated DR, especially recovery from human error, like dropping a collection, you'd often add delayed secondary replicas.
A delayed secondary. How does that work and why is it specifically good for human error?
A delayed secondary is configured to intentionally lag behind the primary by a specific amount of time, say 60 minutes. It still receives the oplog, but it waits 60 minutes before applying each operation.
So if someone accidentally drops the user's collection.
The drop command replicates instantly to your normal secondaries. But on the delayed secondary, it won't be applied for another hour. If you detect the mistake within that hour, you can stop replication on the delayed node, connect to it, retrieve the dropped collection data from an hour ago, and restore it to the production cluster. It's your oops button.
Brilliant. So the DR plan is multi-region replication with majority writes for near zero RPO plus delayed secondaries for fast RTO, recovery time objective from logical errors. RTO target might be 1 to 5 minutes for failover itself.
That's a robust setup, yes. Covers both physical disaster and logical mistakes. Hashtag 4.2 modern MongoDB features. 5.0 over plus to 8.2.
MongoDB hasn't stood still. The sources highlighted several major features added in recent versions, starting with time series collections. What problem do they solve?
They're specifically optimized for workloads involving sequences of measurements over time. Think IoT sensor data, application metrics, financial ticks, logs. These workloads often involve high-volume inserts and queries that aggregate data over time ranges.
And how do they achieve better performance in storage? The sources mention 70–90% compression sometimes.
Two main techniques. First, automatic bucketing. Instead of storing every single sensor reading as a separate tiny document, which has high storage and index overhead, MongoDB automatically groups measurements that occur close together in time and share the same metadata into larger internal bucket documents.
Fewer documents, less overhead.
Exactly. Second, within these buckets, the actual measurement data, timestamps and values, is often stored in a highly optimized columnar-like format. This allows for much better compression, especially for sequential readings, and faster range scans because the engine can process just the relevant time value columns within the buckets.
Very cool. We already touched on online resharding 5.0 plus as the fix for jumbo chunks and bad shard keys. It lets you change the key without downtime. Huge operational win.
Absolutely transformative for managing sharded clusters long term.
Then there's columnar storage 7.0 plus, which sounds related to the time series optimization but is broader.
Yes. While time series collections use columnar ideas internally, MongoDB 7.0 introduced explicit columnar indexes and potentially dedicated columnar storage formats in the future. These are designed for classic analytical data warehousing queries. If you often run aggregations that only need a few specific fields from a large collection, a columnar index stores those fields together, column by column.
So a query summing one column doesn't have to read all the other columns in the documents.
Precisely. It dramatically reduces I/O for typical analytical scans compared to reading full row-oriented documents. It's about making MongoDB more competitive for certain analytics use cases directly within the database.
And finally, integrating with the AML world, vector search 7.0 plus.
This is huge. With the rise of AI, applications increasingly need to work with vector embeddings, high-dimensional numerical representations of text, images, audio, etc. MongoDB added the ability to create specialized indexes, like HNSW hierarchical navigable small worlds, on these vector fields.
So you can query for find documents with embeddings similar to this one.
Exactly. You can perform nearest neighbor searches directly in the database. This allows building semantic search, recommendation engines, image search, and other AI-powered features without needing a separate, dedicated vector database. You can keep your vectors alongside your original metadata in MongoDB. Hashtag tag 4.3 change data capture, CDC, and integration.
Being able to react to data changes in real time is crucial for many architectures. MongoDB's primary mechanism here is change streams. How do they work under the hood?
Change streams essentially provide a real-time, ordered stream of the data modification events, inserts, updates, deletes, replaces, as they happen in a collection, database, or the entire cluster. They leverage the op log. They're basically a filtered, resumable view of the op log tailored for application consumption.
The key for fault tolerance, as mentioned in the sources, seems to be the resumable token.
Absolutely. Every event notification sent via a change stream includes a resume token. This token is an opaque marker representing a specific point in the op log.
Why is it so important for the application consuming the stream to store this token?
Because things fail. The consuming application might crash, get redeployed, or lose network connectivity. Without the resume token, when it restarted, it might have to reprocess events from the very beginning or from some arbitrary earlier point, potentially missing events or processing duplicates. By storing the last successfully processed resume token durably, E2G, in another database or file, the application can restart the change stream exactly where it left off by providing that token back to MongoDB. It ensures exactly once, or at least once, processing semantics reliably.
Makes sense. Now, scaling this up, what are the challenges when you're streaming high volumes of changes, maybe integrating with a system like Kafka using the MongoDB Kafka connector?
High volume presents throughput challenges, ensuring your consumers can keep up. But the bigger integration challenge, especially with Kafka, which often provides at least once delivery guarantees, is idempotency.
Meaning you might get the same change event delivered more than once.
Correct. Due to network retries or Kafka broker behavior, your downstream consumer service might receive the same event notification multiple times. If processing that event twice causes incorrect state, like incrementing a counter twice when it should only happen once, you have a major problem.
So the consuming application must be designed to handle duplicates gracefully.
Yes, it needs idempotent logic. This usually involves tracking event IDs or using database constraints, like unique keys or version numbers, to ensure that processing the same logical change event multiple times has the exact same effect as processing it just once. Building idempotent consumers is critical for reliable CDC integration via systems like Kafka.
Okay, let's wrap up with the practicalities. Making queries fast, keeping data safe, and fixing things when they break. Query optimization starts with indexing. Hashtag tag 5.1 query optimization and index strategies.
And for indexing, especially compound indexes, indexes on multiple fields, the golden rule, the one every developer must know, is the ESR rule.
ESR, equality, sort, range. Explain that.
It dictates the optimal order of fields within a compound index based on how your query uses them. Fields used for equality matches, for example, user ID ABC, should come first in the index. Fields used for sorting, so you'll sort timestamp, should come next. And fields used for range filters, for example, pricey $100 or prefix searches on strings, should come last.
Why that specific order?
Because the database engine can most efficiently use the index that way. It first narrows down the search space using the equality predicates, like jumping to a specific section of the index. Then, within that narrowed section, the data is already ordered by the sort key, avoiding a costly in-memory sort. Finally, it scans the sorted subset using the range filter. Putting fields in a different order, like range first, makes the index much less effective or even unusable for the equality and sort parts of the query.
Makes perfect sense. Following ESR is key. What about achieving peak performance with covering indexes?
A covering index is the holy grail for read performance. It occurs when the index itself contains all the fields needed to satisfy the query, both the fields in the query filter, where clause, and the fields requested in the projection select clause.
So the database never actually has to go and fetch the full document from the collection.
Exactly. It gets everything it needs directly from the index, which is usually much smaller and likely already in RAM. This completely avoids the document lookup step, which often involves random disk I/O and is a major source of latency. Covering indexes are the goal for your most frequent performance-critical queries.
But there's a dark side to indexes. Index overhead. We can't just index everything, right?
Definitely not. Every index you add comes at a cost. Primarily, write amplification. When you insert, update, or delete a document, MongoDB doesn't just modify the document itself, it has to update every single index that includes that document.
So more indexes mean slower writes.
Significantly slower writes, yes. More indexes also consume more RAM to stay cached for reads, and more disk space. The general guidance is to be judicious. Aim for a small number of highly effective indexes per collection, the sources suggested ideally 5, that support your common query patterns, leveraging compound indexes and ESR. And critically, monitor index usage, index stats, and drop indexes that aren't being used. Index sprawl kills write performance, hashtag tag 5.2 concurrency, transactions, and write conflicts.
Let's revisit transactions, specifically the most complex case from the sources.
Yeah.
A multi-document transaction that spans multiple shards, like transferring money where the debit is on shard A and the credit is on shard B. How is atomicity guaranteed across that distributed boundary?
This requires coordination. MongoDB uses a mechanism conceptually similar to two-phase commit, 2PC, orchestrated by a transaction coordinator, which usually runs as part of the Mongos or potentially config servers.
Okay, phase 1.
When the application issues the commit transaction command, the coordinator enters the prepare phase. It sends a prepare command to all participating shards, shard A and shard B in our example. Each shard then internally prepares the transaction and makes sure it can commit, acquires necessary locks, validates constraints, writes commit information to its local journal. It then votes yes, prepared, or no, abort, back to the coordinator.
What happens if even one shard votes no or fails to respond?
If any shard votes no or times out, the coordinator immediately sends an abort command to all participating shards. The transaction is rolled back everywhere, guaranteeing atomicity. Nothing gets partially committed.
But if all shards vote yes in the prepare phase?
Then the coordinator enters the commit phase. It durably logs the decision to commit and then sends a command to all participating shards. The shards then make the changes permanent. Even if a shard crashes after voting yes, but before receiving the final commit, the coordinator knows the overall decision was commit, and recovery processes will ensure the commit eventually completes on that shard. It's that two-phase coordination that guarantees all or nothing across shards.
Complex, but robust. Now shifting to a common performance killer. Memory pressure and cache eviction. What happens when the database's working set just doesn't fit in RAM?
This is often described as hitting the cache cliff or the death spiral of performance. The working set is the portion of your data and indexes that are actively being accessed by your application. If the size of this working set significantly exceeds the amount of RAM allocated to the WireTiger cache,
Bad things happen.
very bad things. The cache starts thrashing. WireTiger is constantly forced to evict pages from the cache, potentially useful hot data, to make room for other pages that need to be read in from disk. Because the working set doesn't fit, pages that were just evicted are often needed again almost immediately, forcing another read from disk.
So you get a massive increase in disk I/O.
Huge increase in slow physical disk I/O, page faults. The disk becomes the bottleneck, latency skyrockets, throughput plummets, and CPU might even look idle because it's always waiting for disk. It can cripple the entire system.
What are the solutions when you hit this?
It's a tiered approach. First, the obvious. Increase the cache size. Give WireTiger more RAM, if possible. Second, reduce the working set size. This is often about optimization. Better indexing, especially covering indexes, so queries access less data, optimizing data models, maybe archiving old, unused data. Third, if the active working set is genuinely just too large for a single node, the only real solution is to horizontally scale by adding more shards. This distributes the working set across more machines, each with its own cache. #tag 5.3 security implementation.
Finally, let's cover security. Protecting the data requires multiple layers. Start with data on disk, encryption at rest.
This is table stakes now. WireTiger supports transparent AES 256 encryption of all data files on disk. You configure it typically using an external key management infrastructure. KMIP compliant servers or a cloud provider KMS like AWS KMS, Google Cloud KMS, Azure Key Vault. MongoDB fetches the encryption keys from the external KMS at startup.
So if someone steals the physical disk drives, the data is just encrypted garbage without the keys.
Correct. It protects against physical theft or direct access to the underlying storage volumes.
But what about protecting sensitive fields within the database, even from privileged users like DBAs? That's where client-side field-level encryption, CSFLE, comes in. This sounds more complex.
It is significantly more complex, but also much more powerful. With CSFLE, sensitive fields like credit card numbers, social security numbers, PII, are encrypted by the MongoDB driver within your application before the data is even sent over the network to the database server.
So the database server itself never actually sees the plaintext data for those fields.
Never. It stores and processes only the ciphertext. The driver automatically encrypts on write and decrypts on read, using keys typically managed via the same external KMS infrastructure.
But the sources mention a key feature. You can still query some of these encrypted fields. How is that possible without decrypting everything?
It uses different types of encryption. For queries needing exact matches, for example, find the user with SSN encrypted value, CSFLE uses deterministic encryption. This means the same plaintext value always encrypts to the same ciphertext value using the same key, so the database can index and match the ciphertext directly.
But that deterministic property must have limitations, right?
Absolutely. Because the same input yields the same output, it leaks equality information. If two documents have the same encrypted value in a deterministically encrypted field, you know their original plaintext values were identical. More importantly, you cannot perform range queries, greater than, less than, substring searches, or case-insensitive searches on deterministically encrypted fields. Those operations would break the encryption's security properties. For fields needing those types of queries, you'd have to use randomized encryption, which is searchable only via decrypting on the client side after fetching, or not searchable at all, server side.
So CSFLE requires careful planning about which fields need which type of encryption based on required query capabilities. It's not a magic bullet.
Definitely requires careful design.
Okay, besides encryption, what are the other essential security layers?
Two big ones. First, role-based access control, RBAC. This is about enforcing the principle of least privilege. Define roles with specific permissions, read, write, create, index, etc., on specific databases or collections, and assign users or application credentials only the roles they absolutely need. Don't connect your app as a super user. Second, auditing. Configure MongoDB to log significant security-relevant events, logins, successful and failed, user role modifications, DDL changes like dropping collections, potentially even access to sensitive data. These audit logs are crucial for compliance like GDPR, HIPAA, SOX, and for forensic analysis if a breach occurs. #tag out her DAC.
Wow, okay. We have gone through an incredible amount of details synthesizing those 17 source topics. I think the core theme, the L6, L7 takeaway, is really internalizing those deep connections between the theory, the engine mechanics, and the operational knobs.
Absolutely. If we boil it down, MongoDB chooses consistency in CKP by default, using Raft-inspired quorum math for safety. Its performance relies heavily on WireTiger's MVCC for concurrency, and its scalability hinges on smart sharding and chunk management with online resharding as a critical escape hatch.
And we kept coming back to trade-offs. Every single decision. Use W majority for near-zero RPO. Great, but accept the latency hit and potential unavailability during partitions. Use W1 for speed. Fine, but understand and mitigate the data loss risk.
Exactly. For you, the listener, moving to that higher engineering level isn't just about knowing what command to run. It's understanding the why. Why does linearizable reads cost more? Why does a bad shard key cause jumbo chunks? Why does a long transaction kill performance? It's about grasping the inherent compromises in any distributed system.
So here's a final thought to leave you with, building on everything we've discussed. When you design your next system on MongoDB, or any distributed database really, actively ask yourself, where am I on the CIP spectrum for this specific feature? Are my critical financial transactions worth the latency of cross-region majority writes and linearizable reads? Or is the user's like button click acceptable with W.1 and eventual consistency for maximum responsiveness?
That conscious evaluation of the trade-offs, balancing user experience, performance, cost, and data safety, that's the essence of distributed systems architecture. Understanding not just what MongoDB can do, but why it forces you to choose.